TTV, what's up? 12 o'clock in the morning and I have a school. Oh, okay. Go sleep. No need to watch my stream because I'm gonna stream whole night. Also, I'm streamer's moderator and he was on Omegle and a guy was stroking on Omegle, so he has to put the stream off, lol. God, such a weird situation, right? We all saw it on the stream, yep. And I hope YouTube is not blocking the stream then. Oh God. Hello, my friend Nick BS. Hi. How are you doing? I'm doing okay. Good. Not too bad. Come to Brazil. I would love to. He was even Indian. It might have been you. Oh my God. You're doubting me? Really? Really? First of all, I'm not on Omegle. Second of all, I was not even there. I just came now. Best night ever. Oh God. This is not at all a best night. What are you doing on stream right now? Fixing something, error, building something. Oh, how do you know all this? How do you know all this? Are you are you some agent looking at my screen or something? He even raised up a girl and got her Insta. Oh my God, really? What's happening in this world? Yes, from America and he's from South Africa. No, I just looked at your YouTube channel and based off the sounds you're making. Oh, yeah, yeah, yeah. You're right. You will hear all the keyboard sounds. So you're right. Don't worry, I don't know your Google history. I mean, even if you know, it will be DeepSeek, nothing fancy. For today or for this month, it will be either AI or coding or programming or something like, oh, where can I get some cheap food or something? Okay. Nothing interesting for you. Trust me. Do you know the company Take Lot? No, I don't know. Oh, Google them. I brought my I bought my PC there, but still waiting, you know. Oh, okay. You're a programmer. Oh my God, I'm trying to learn something about coding and these stuff. Interesting, yeah. I'm a programmer, not like as pro as these guys, AI guys. Hi, sorry to ask, but what are you doing? I'm actually studying technology. I'm studying low-level technology tonight. Thanks. Thank you so much. It is just so hard for me, not gonna lie. It's very hard. It takes years and years to become good at something. I'm still learning. You see my notes? Okay. Every day, every day I write things. Okay. Every single day I write things just to keep learning because I cannot, I cannot remember everything in my brain. Hey, XX, how are you doing this day, Low? Hey, you are so cute. Really? Okay. Simp. Oh God. I hope you will be the person you want to be. Wow, that's what a line. I'm very inspired. That's funny. Keep it up, my friend. You are doing great. Enjoy your life as much as you can and be positive. Okay. Thank you so much. Drinking coffee in the middle of night. I hope you won't fail. It's not an exam, huh, but it's very important. the learning part is very important. I'm not tired, but if I sleep now, I'll only get 7 hours of sleep, then I'll be tired. Oh my God, it's a very, very complex problem. Try DeepSeek. Ask DeepSeek the same question, what should I do? And DeepSeek will reply nicely. I might just go, sorry, but I'll have to sleep. It's one of the things. Peace. Good night. Good night. Thank you so much for joining and have a great sound sleep and wake up fresh tomorrow. That's all I can wish for.
Uh, deferred vertex shading for an hour, then it's way too little to cover all the details, and it's way too much to just briefly touch on it. So I decided that I also wanted to include a bit about the evolution here of vertex shading in Mali, and that will hopefully give you some understanding of why some things are like they are and how we got here. So let's see. Yeah, so it's not the intention of this presentation is not to cover everything, and I'm purposely omitting a lot of details, and I'm trying to simplify so that it should be possible to listen to this and understand most of it without much knowledge about vertex shading or Mali. So hopefully someone finds that interesting, and also covering some of the history, hopefully someone will find interesting. So I'll just jump into it. Just to make to set the scene here. What's the goal of the vertex shading, or where does the vertex shading fit into all this? I got a diagram from the Chronos website showing the rendering pipeline. So I thought I'd just talk a bit about the first part of that rendering pipeline. And you can see this diagram on the right side of this slide, and it's basically a set of steps that needs to be taken, where you start with the application providing some data that should be used by the GPU, and vertex data is one of them. Topology information like the primitive type and index array, some shaders and some texture data and other things. And the rendering pipeline is defining this so that it will produce, it will process that data provided by the application and produce the final frame buffer. It's as simple as that. And then we split this pipeline into two main parts. Where one part, the first part, is the geometry processing, and the second part is the fragment processing. And the big difference between them is that on the geometry processing part, you process every vertex or every primitive, while on the fragment side, you process every fragment produced from those primitives. And those fragments are created in the raster, so that will sit on the border between those two parts. The vertex shader, or vertex shading, it's a program, user-defined program, where the application will set up an ordered list of vertices, which is sent to the pipeline. The vertex shader is run on every vertex, and it produces a new vertex for every input vertex. And the vertex shader then will do whatever the user has defined, but it's typically rotating, scaling, transforming, and in the end you have a position which is in the right space, so that the frame. So you can put it on in a frame buffer on the screen. Vertex shader has to output a position, and it can output any number of user-defined vertex attributes, and we also use the name bearings for those vertex attributes. Then once you have run the vertex shader and you have produced the output vertices from that one, the next stage in the rendering pipeline is vertex post-processing, where you typically take the array of output vertices, you take the topology information, and you output primitives. And for the input, you could have, for instance, a triangle strip, which contains 3 vertices for the first triangle. Then you have 1 additional vertex for every triangle after that. So they are connected with a shared edge. But on the output, you will see individual triangles. And that makes the rest of the pipeline a lot easier. You also perform culling, and the typical one is the face culling, where you remove all the primitives that face away from the viewer or from the camera. We also perform other types of culling, like we have something called sampler tiling, where we remove primitives that are so small that they never touch any sample points. And in the rendering pipeline, the next stage after this is the rasterizer. And I won't cover anything from the rasterizer and beyond in this presentation, as I'm focusing on what happens before that. But Mali is a tile-based GPU, which means that it processes tiles and not the whole frame buffer. So we need to split all the primitives into tiles, which can be processed by the shader core. And this process of splitting or tiling is performed by the tiler. So after we have done the vertex post-processing, the tiler will create polygon lists, which is basically a list of primitives for each tile in the frame buffer. So when the fragment job starts, it will start by reading that list to see which primitives should be drawn for this tile. So if you look at where it come from, the first product, which was well, it was from before before Phalanx was acquired by ARM. We had several products, and I think Mali 55 was probably the big one there, Mali 55 and Mali 110. This was an OpenGLES 1.1 GPU, which means that you didn't have the programmable shaders, but instead you had a set of fixed function units. There were no hardware support for vertex shading. So software had to iterate through all the input vertices and perform the shading. And since the CPU is relatively weak, a lot of optimizations had to be performed to get some decent performance. Still, the content wasn't that complex. And if you look at the screen sizes, it was smaller than VJ, so QVJ, supporter of a VJ frame, and maybe QCIF, I think something was called. Power consumption wasn't a big concern. but everyone was very concerned about area. And the main reason for that was everyone wanted a GPU, but they hadn't put any GPU in their area budget. So they had to squeeze in a GPU at as low cost as possible. And of course, there were some obvious problems there. Doing this on the CPU wasn't didn't scale very well. And of course, the power consumption wasn't impressive. And there was a lot of code to optimize this. So after the ARM acquisition, so we became part of ARM, we started to work on the Mali 200, Mali 400, and eventually Mali 450, which was an OpenGLES 3.x pipeline or GPU. It had the programmable shader support, and it had MMU and L2 cache like we see in the current products. We didn't have the unified shader, which we have today, so we had two different shader cores. We had Mali GP, which was the geometry processor, and we had Mali PP, which was the pixel processor. And Mali GP consisted of a vertex shading core and a polygon list builder, which is mostly the same as the tiler we have today. And then you had three stages where one stage you ran the vertex shading inside Mali GP, you performed the tiling in the polygon list builder, and then you sent everything to Mali PP for fragment shading. So it was looking a bit more like you're doing today, where we process those vertices in hardware. And it was quite efficient. We spent a lot of time to optimize the hardware so that the area cost was as low as possible. If we could cut some corners, we cut those corners. And it was very efficient. But it wasn't efficient in cases where the input wasn't optimal. And one example of that is if you have a very large vertex array, but you're only using a couple of those vertices, you are shading all those vertices and then never use them. And one optimization that the DDK did for this was they had to scan through the index array, try to find blocks of vertices that were never used, and try to avoid shading them in the vertex shading class. So software wasn't too thrilled about that, but they didn't know better. Also, having three stages meant that scheduling was a bit problematic, and you could easily get some bubbles where only one of the stages were running and the other stages were just sitting there waiting for some output. So performance wasn't stellar. When OpenGL 3 came, we had a lot of discussions about upgrading Mali 450 to OpenGL 3. And the reason was that Mali 450 was extremely popular. And it was very small and very efficient. But we found that upgrading it was a too large task, and we had to make sacrifices, which basically removed all those optimizations we had worked hard for a long time. So we basically moved over to Meteor at that point. So the Meteor product was the first OpenGL 3.x GPUs. Data flow is very similar to Mali 400 and 450, but you have the unified shader core. So you still have those three stages where you did the vertex shading, then you perform the tiling, and eventually the fragment shading. So very similar to Mali 450. I'm going to show some diagrams here showing the data flow, and I tried to simplify it as much as possible. So this is what we call legacy tiling, which was what we did for the first Midbar products, and it was removed, or it was deprecated some years ago, and it was removed 1 or 2 years ago. So it's fairly recent. And in legacy tiling, of course, the application will create a vertex array and an index array for the GPU. And just to make sure that everyone understands my figure, the rectangles are the different units, and those cylinders are storage in main memory. So after the CPU has created those input vertices and the index array, you run the vertex shading stage, where the shader core will read through all the input vertices, and write them back out to an output vertex array. Once that is done, the timer can start, and it will start by reading the index array. Then it will read all the vertices that are referenced by the index array, and it will create a polygon list for consumption of in the fragment processing. So when you're starting the fragment shading, you will read the polygon list, and you will read the vertex data needed to build those primitives that are listed in the polygon list. A lot of other things happen after this, but it's not relevant for what I'm trying to show today. So I haven't included any further steps here. So there were some problems with this. Especially, we saw over time that complexity increased and the primitive count increased. and well, basically everything performance related increased, which meant that bandwidth increased and of course the memory footprint increased. And we still depended on the DDK for optimizations to remove as much work as possible. And then I don't remember at what time we introduced index-driven vertex shading, but Heimdall maybe. That one was turning the whole data flow a bit upside down. So the tiler is in charge of the vertex shading instead of something happening before you start the tiler. And the tiler will request vertex shading from the shader core on demand. So as it reads the index array, it will figure out which vertices it needs, request vertex shading for that, wait until the shading is completed, and then it can use those vertices. And of course, there are caches around, so you don't shade the same vertex many times if they're using several primitives. We also split the vertex shading into two parts. As I already told you, a vertex shader needs to output a position, and it needs to output the vertex attributes or variance. But for the tiler, we only care about the position. The variance is used during the fragment stage. So by splitting the vertex shading into two, we could have one position shader, which only produces the position, and then we can have the variance shader, which produces all the vertex attributes. The benefit from this is that we usually call a lot of primitives, and 50% is probably a conservative estimate because half of the primitives will be pointing away from the camera. So that means we can probably reduce the variance shading by 50% by doing it after checking visibility. Another benefit from this is if you have a really large vertex array with thousands of vertices, but you have a small index array, so from those thousands of vertices, you may be building 20 primitives. Then you don't need to run through the whole vertex array because you only shade those vertices that you need. And that also means we can remove those optimizations from the DDK, and everyone is happy. And the big benefit from this is bandwidth reductions. You still have to read the input vertex data, but you only write out the visible vertex positions or the variance. And in the end, you will only read the vertex data once. So a big improvement there. The same kind of figure as I showed for the legacy tiling. You still have the application providing the input data. You start by the tiler reading the index array and sending shading requests to the shader core. The shader core, well, there's one arrow missing here. So the shader core will read the input vertex data and then return that shaded vertex or shaded position back to the tiler. The tiler will then build the primitives and perform the culling. And if a primitive is visible, it will write out the position and it will request the variance shading. The shader core running the variance shader will then, of course, read the input vertex data, shade the variance, and write this out to memory. And when you start the fragment job, it's the same as with legacy that you read the polygon list and you read the necessary vertex data and process those primitives. There were still some problems with IDS flow, and one problem was the memory footprint, because we for every input vertex array, we need to have a similar output vertex array, and the output vertices might be larger per vertex than the input, or it could be smaller as well, but you still need to allocate memory for all the vertices, and it will end up as a sparse array because you only write out those visible vertices, so we are wasting a lot of memory. And since you need to do this worst case allocation all the time, it's painful for DDK, which needs to handle low memory systems and all kinds of applications. So the next step we had there was the IDVS with memory allocation. It's very similar to the regular IDVS flow. The difference is that the output vertex data is not written to a pre-allocated vertex array, but the tiler will allocate memory from the tiler heap and write out those vertices as they become visible. So instead of having a sparse array, you can pack everything together and you will have only the visible vertices contributing to the memory footprint. We already had the tiler heap, so this was a big improvement for the DDK, but the way we handled the heap was a bit problematic. The reason was that we had one enormous chunk of memory that was working as a heap, and we didn't support properly when you actually run out of memory. So after a couple of iterations, we have this chunked heap today, where the heap consists of chunks of memory, and the driver basically remove chunks as they are used and add new chunks to the end of that list of chunks. And it fits a lot better with the model they are using there. Still, we haven't solved all the problems. Up until this stage, tiler performance wasn't a big problem because we were usually feeding data into a limited number of shader cores. But as we saw that the shader count increased, we had a lot harder performance requirements, and we had to spend a lot of time to improve performance. But at the same time, there was a shift from just performance or performance density to power consumption. And everyone has been working on reducing the power consumption. And for us, the tiler itself is not a big contributor to the overall power consumption, but external memory accesses is a large part of that. And there's a lot of geometry bandwidth in most applications. And the only way we can reduce the bandwidth, because we need to read the necessary input data, and we are producing polygon list, and you also populate the output vertex data buffer. And the polygon list, well, both of them are just temporary data, which is living until the fragment job has completed. Then we just get rid of it. If we could keep that data on chip while performing the fragment job, we would basically eliminate all external bandwidth. But since the tiler runs before the fragment job, and we don't overlap the tiling with the fragment job, it's really hard to keep everything on chip because we don't know how much data we need to produce. So instead, we are looking at this deferred vertex shading, where the big mantra is don't write out any temporary data. We are not able, at least for now, to remove the polygon list writes. But the polygon list is relatively small compared to the actual vertex data. And we intend to avoid writing out the vertex data by recomputing it when we need them. So that gives us the DVS, or deferred vertex shading. You start the same, the application will provide some input data. The tiler will read the index array and figure out which vertices is needed. Then it will send the position shading request to the shader core. The shader core will also have missing one arrow, read the input vertex data for that vertex and perform the shading and return the position to the tiler. The tiler can then perform so build the primitives, perform the culling, and decide if the primitive is visible or not. And at that point, it will only write out the polygon list. With IDVS, it would also write out the position, and it would request variant shading so that you could also populate the vertex array with all the variants. And you can also see that I removed that cylinder with the output vertex data. Then when you start the fragment job, the shader core will start by reading the polygon list. And instead of reading the vertex data needed, it needs to produce that vertex data. So it will send an internal vertex shading request. And the vertex shader will then read the input vertex data, perform the shading, and return the shaded vertex to the part where to the fragment frontend. And then it continues as normal. So the main benefit from this one is, as you can see, there's no output vertex data. And we have removed the big offender on the geometry bandwidth. There are a couple of problems with DVS. So for instance, the shader core will process one tile at a time. And if you have a large primitive, you have the same 3 vertices needed in multiple tiles. And since it's not possible to reuse vertex data across tiles, you basically need to recompute them. And if you have a primitive covering the whole screen, you end up recomputing those vertices thousands of times. And that would destroy performance. And if you look at the number of large primitives, it's relatively small. But those large primitives would contribute to a lot of the problems we see. Another problem is that the load store cache is used for temporary storage, which is great, but we have a very limited storage capacity. So to make the pipeline busy at all times, we need to make sure that we have enough outstanding vertex shading requests so that we can feed the shaded vertices to the fragment frontend so that we can keep the rest of the pipeline busy. And since we have a limited storage capacity and the size of the data for a single vertex depends on the amount of variant data, you could end up with some draw calls where you have a lot of variant data and you can hardly fit more than 32 vertices on this local buffer. And you would basically run for a very short time, need to wait for more vertex data to come back, and then you would have lots and lots of bubbles and you would see terrible performance. And the solution to that is to combine DVS and IDVS. So if you have a large primitive, and we found that larger than 4 tiles, then you, larger than 4 tiles is a good compromise, then you process them as IDVS primitives. If there's a lot of variant data, you process them as IDVS primitives. And we also have some cases because DVS is not supporting the most complex geometry flows, and like multiview is not supported with the DVS. But apart from that, the rest will be DVS primitives. There's been some benchmarking done. So CT had an investigation where they produced the initial results, and I haven't seen any more recent results. But I think the main takeaways here will also be valid for more recent or future results. And you can get more details from this investigation if you look at the link to the conference page. But what you see is that almost all the primitives are DVS primitives. So 98% in average are DVS primitives. And we reduced the geometry bandwidth quite a lot. And since geometry bandwidth is a big part of the total bandwidth, we also see a really good improvement or reduction in the total bandwidth. Most of the tests are around the same performance or slightly faster. We have some cases where we are a bit worse than with the IDVS. But in general, it shows a very significant improvement. One thing with DVS is that it's a very large project. It involves a lot of CTTs on the hardware side. It's also involving a lot of other teams. But from the hardware point of view, you have the tiler, of course, is involved because the tiler is doing something different. And the tiler team also has the ownership of the new block in the system, which will ensure that vertex shading is performed before sending the primitives to the fragment frontend. Fragment frontend is also involved. We have a mix of IDVS and DVS primitives, so you basically have two different buffers that needs to be accessed, and you need to make sure that you track which buffer you should use. PPP is involved. That's mainly the FSDC, SEM. I think that's the main ones. The engine is involved. The attribute pipe needs to calculate the addresses into the buffers for each vertex, and you have two buffers, so you need to select the right buffer and perform the right address calculation based on that. Memsys is involved. That's mainly because there's a new path from the load store cache to the fragment frontend for vertex data. There are some changes to the various interfaces between the different blocks and some architecture spec changes, which involves the job control. And of course, it also includes top level and some other groups. In addition, we have found that we require a couple of other changes to make this work efficiently. One is the unified shader. And the unified shader is support to define what kind of shader output you want to have when you are invoking a shader, which means that we can have one unified shader. And when we invoke that shader, we can tell we want to have the positions, or we want to have the variance, or we want to have both of them. That allows us to have a single shader for all the different variants, instead of having a varying shader, a position shader, and a full shader, or being forced to issue both the varying shader and the position shader in the DVS vertex shading stage. Also, we need to have larger tiles. You hopefully remember that I said tiles or primitives larger than 4 tiles will be IDVS primitives, and the reason for that is the reshading. And by increasing the tile size, we are basically reducing the amount of reshading, and it will allow larger primitives to be DVS primitives. So that was everything I had for this presentation. I'm open for questions.
Thanks a lot. So if you have any questions, feel free to unmute yourself or write in the chat, and I can read it out.
Yeah, I have a question. Can you hear me?
Yeah, go for it.
Yeah, so with DVS, there is a certain compromise. So when Tyler shades positions and then discards them, and then positions are reshaded on fragment stage, so was it considered that the position data is still written out and only the variants are shaded on the fragment stage?
Well, it's a bit hard for me to answer that one because CT has done a lot of investigation before we got that one. I guess writing out positions but not producing the variants would be a compromise, but I'm not sure if it would be a good compromise because you, in almost all cases, you would need to run the variant shader as part of the fragment stage. And the main issue with running any vertex shader before the fragment, or as part of the fragment stage, is that shading takes a lot of time, and you need to make sure that you can fill the pipeline. So I think you would need to basically do the same as we do today. You would save some instructions on the vertex shader because you don't need to run the position part of it. But the cost of running those extra instructions compared to reading the positions would probably cancel each other out. I guess CT needs to ask if they consider this one, but I don't find it a very compelling solution. It would include all the complexities, but only half of the benefits.
Yeah, I just wondered if it was investigated, and maybe we have numbers specifically on this faculty.
Okay, there are a couple of questions on the chat as well. Did you consider using flexible tile sizes?
Well, I guess we have some kind of flexibility in the tile size. We can reduce the tile size. It's hard to increase the tile size because you have some physical buffers backing this up. But you can reduce the effective tile size. I'm not fluent in those tile size discussions, but it's possible to have smaller tiles if necessary.
Okay. Next question is, how does this solution compare to vertex shading solutions implemented by other mobile GPU vendors?
I know very little about other solutions there, but I can answer in a more generic way. So we have a tile-based GPU where we do this in tiles and in several stages. While for an immediate mode renderer, you would have some kind of a post-transform buffer, which looks a bit like what we do with DVS, where you produce the primitives or the vertex data, and you put it into a post-transform buffer, and then you can run the rasterizer and the fragment shading. The good thing about the immediate mode renders is that the data flow is much more like the rendering pipeline, and they don't have all those different stages and they don't need to store out this vertex outputs. The bad thing is that they get all the cost on the fragment side. So the frame buffer and depth buffer and everything is too large to fit on chip. So they need to store this into external memory. And I'm sure they have lots and lots of optimizations to reduce the cost of that. But in general, Mali have very, very little fragment bandwidth compared to immediate mode renders, but they have a lot more geometry bandwidth. And I guess you could argue that the immediate mode renders are moving a bit towards tile-based rendering, and the tile-based renders are moving a bit towards immediate mode rendering. So I guess in the end they will. I won't say they all will look the same, but they are converging, I think.
Okay. There's a question from Chris Basley, I think. You have raised your hand. You want to unmute yourself?
Hello, do you hear me?
Yep.
Yes.
Yeah. Perfect. I also put this in the chat, so sorry if that means I jumped the queue. I'm very interested in software renderers from the 1980s and 1990s, and I'd love to speak to you about those sometime, but I don't really think it's pertinent. My question was hopefully a bit more pertinent. Is this a solution that's specific to tile-based hardware renderers, given that, if I understood you correctly, transformed vertex coordinates are still shared between different polygons in the same tile? And again, if I understood you correctly, they are still written to temporary memory, albeit on-chip memory.
I'm not sure I understood your question. I think I understood the description, but can you repeat the question?
I think you said something like the transformed vertex coordinates are written to cache, presumably on-chip, as part of the GPU, so that they can be shared between different polygons within the same tile. Is that right?
Yeah.
So there's nothing magic about it. You are still writing them out to memory.
Yeah. So on the tiler side, we have a vertex cache. So when we request position shading, we will put that into a cache. And if you have multiple primitives within a reasonable period that use the same vertices, they will exist in the cache. And on the fragment side, with the DVS vertex buffer, we basically have the same. We use the load store cache for temporary storage. And if we have multiple primitives that use the same vertex within a reasonable amount of time, we will use the cached version of that. And you can take a look at the reshading rate, because even if you have already shaded a vertex, it might be evicted from the cache before you need it. So in those cases, you will see that the reshading rate is increased, and that could have a bad impact on all PPA metrics. But we have seen that it works fairly well.
Okay. So supposing we only have one tile and it's the size of the screen, none of this makes any sense, does it? Because you could never possibly have a large enough cache.
No, so then you would have an immediate mode render, and you have different problems.
Yeah, okay. Just making sure I understood. Thanks.
Okay. Next question is from the chat again. It's about the motivation for unified shaders. Is it to be able to dynamically choose between IDVS and DVS depending on tile coverage, or is it related to some instruction cache aspect?
So the main motivation, I think, is software related or compiler related. With DVS, we need different or more variants of the vertex shader. So the application will provide that vertex shader, which the compiler needs to compile into something that Mali understands. And as I've understood, I'm not an expert on this, this takes quite a lot of time. And the more variants you are adding, the more time it takes. So software has been very keen on reducing or keeping the number of different variants as low as possible. And one option we were looking at, if we didn't get the unified shader, was to have a position shader and a varying shader. For all primitives in the beginning of the tiler, you will run the position shader. if you decide a primitive should be an IDVS primitive, you run the varying shader from the tiler. And when you start the fragment pass and you need to run the vertex shader there, you need to issue or invoke both shaders. And it's not a big problem, but you suddenly double the amount of tracking you need to do, because you need to make sure that both the position shader and the varying shader has completed before you can pass the primitive on.
And it's even worse than this. There are some attributes that the position shader will output when you run it as the position shader, such as, for instance, point size. That's required to be able to do tiling correctly. But we don't need that when running it as DVS, so you get yet another set.
Yeah.
By having this conditional, you also actually solve some other issues we wasn't really planning to solve. But the Glass had an issue where it's valid to write to point size even if you're drawing triangles. And we had no place to store the point size, so we needed some nasty workarounds. Now you just check, do I need point size? And if you don't, you just skip that part.
Thanks for the answer. Next question, is it possible to have a tile which has vertices which have some candidates for IDVS and some for DVS? And if so, is it possible to run into scenarios which need the output vertex data, but it's not available to the DVS being done?
I think I understood the question, but please correct me if I'm wrong. So the DVS support is something we can enable or disable per draw call. So for instance, if you have a draw call where you use multi-view, or it's part of a more complex geometry flow, you can disable DVS. And you basically have two options here. You have this force the early shading, which is IDVS, or you allow to mix it. And for any draw call, you can mix and match as you want. And it could give you some kind of strange effects. Like if you have two primitives where one is fairly large and the other is small and they are sharing an edge, so they share two vertices, then you have the large primitive will be forced to IDVS, and you will produce the vertex data for those three vertices. The next primitive will be a DVS primitive, and you need to reshade them in the fragment shading pass or stage, because you don't have any link to the original vertex at that point. And this is something we are looking at for the future optimizations. If you have already produced the vertices as IDVS from IDVS primitives, you could potentially prefer to use IDVS for the small primitive as well. But this is something we'll look into in the future. But right now, you can mix and match as you want between DVS and IDVS.
Okay, so I think my question was more, thinking about the reverse one. So if you, let's say you have the opposite case where you have you've done DVS first and you've not produced the output vertex data, is it possible to have a strange scenario where we expected the output vertex data to be there because the next one is IDVS?
Okay, no, so if you look more into the details of the fragment frontend there, you have the polygon list reader, which is followed by what we call the VCU, so the vertex control unit. And that one contains a large FIFO to store primitive information while you are doing the vertex shading. And both DVS and IDVS primitives will end up in that FIFO. This FIFO only includes basically what you see in the polygon list, which is the indices for the vertices in that primitive. And on the output of this FIFO, you have a check. Is this an IDVS primitive? Well, then you just pass it on. If it's a DVS primitive, you check, have I produced the vertex data needed for this primitive? And if you haven't, then you are stalling the whole FIFO. So all the primitives will be output in the same order as they are received. And we do a check for every primitive that we have produced the vertex data before we pass it on.
Okay, that makes sense. Thank you.
Okay, maybe then the last question before we reach the top of the hour. Have you considered some sort of per tile visibility buffer to avoid performing variance computation for fragments that won't contribute to the image?
I must admit I haven't considered it too much, but there's a lot of effort going on in, especially in CT, about this. So I think, well, the last work I've seen is from Tord.
I'm on the call, by the way. Hello.
Hello. You can answer that one.
Yes. So you're in luck because this morning I got the data where I've gone, build a visibility buffer, and then, as part of fragment shading the tile, you just do run all the fragment shaders or run all the fragments up to the point where you know visibility. And then you store the primitive ID in a visibility buffer, and then you go back to the top of the tile once you get to something transparent or the end of the tile. And then you start over, and this time you're sort of doing the full fragment shading, but you're only shading the things that are visible in the visibility buffer. And the results I got back this morning was what happens if we only do position shading in the first step and just only do attribute shading for the visible things. And I don't have complete results yet, but at least I have a working model, and for the content I get back, it seems like I've reduced the number of load store cache instructions by 15% compared to plain DVS, which is kind of cool.
Yep.
And that's on top of a whole lot of culling fragment work like texturing and FMAs and so on. So I'm anticipating I'll have to do some donuts of my own in not too long to explain all of this, but there's some really exciting results coming in that area.
Okay, I'm looking forward to that. There is 2 more questions remaining. Do you have time, Frank, to answer them?
Yeah.
Okay, let's go over them then. Any data on how IDVS vertex and tiling time compares to DVS tiling in the same render pass? In theory, it should be shorter because it doesn't do attribute shading, but how much?
So if we have any performance data for this, or can you repeat that question?
I'm not sure if the person who asked the question is still on the call.
Yeah, can you hear me?
Yeah.
Okay, so with DVS, we have a series of IDVS jobs and then the fragment job, right? And the IDVS job takes a specific amount of time. But with the DVS flow, we have a shorter, the vertex tiling is supposed to be shorter, right? And the biggest amount of work will move to the fragment job. So I was wondering if you have any data on how shorter it might get, because we are seeing content that, especially in Valkan, that doesn't properly set barriers. So it creates bubbles. So the bigger the vertex tiling is, the bigger the bubble, because it cannot run something in parallel.
I don't think, well, we probably have some numbers. Most of the numbers I've seen is the total GPU cycle count, which is in most cases slightly better. But for the tiler part, you remove some of the potential bottlenecks. First of all, you do less variant shading, but that doesn't directly impact the tiler runtime, because it will just issue the shading request and then move on, so it will never wait for the response here. And you could argue that this takes a cycle. But you remove a lot of the brights from the tiler, and we have seen cases where the write back is a bottleneck. And when you suddenly don't write out any position data, you remove that bottleneck. And the only thing the tiler will write is the polygon list and the pointer array. So it has a pointer cache, and people need to read and write from that one. So my assumption is that, yeah, we should see a fairly decent performance improvement on the tiler. And if you also look at the other types of improvements we have done lately, so for TERS, we have basically tripled the tiler, at least the architectural numbers, where we previously needed 3 cycles per triangle. Now we need 1 cycle per triangle. And if you look into what we are doing for Crake, we will basically double the performance again, where we are creating triangle pairs and process a triangle pair per cycle. So you should see even better performance in Crake.
Cool, thank you.
Right, last question is from Gus. Since it is likely that neighboring tiles will share some of the vertices, would it be possible to ensure neighboring tiles are likely shaded on the same core, so a per core cache for variance could be used?
Yes, but I guess this is a bigger question than just the DVS shading. The caches are for all types of data, and I don't have a good view into what has been done on this scheduling, but I know that it has been something that has been on the table for many years. And if DVS is slightly changing the balance there or not, I don't know, but it's something we'll try to figure out when we get the complete model up and running and we get hardware RTL running.
Okay, I think that was all the questions in the chat. I would say thanks very much, Frank.
Well, thank you all for joining our lecture for interactive computer graphics. Today's lecture is going to be on an exciting topic that is going to be, drumroll, GPU ray tracing. Now, this is not a very new thing, actually. People have been implementing ray tracing on the GPU for quite some time now. Like, as soon as we had programmable GPUs that we could implement anything that we want, one of the first things that people wanted to implement was ray tracing, so they did that. But this is becoming new in the sense that now we have direct hardware support for GPU ray tracing on a larger scale than we did in the past. So that's definitely something that's emerging in that sense. All right, let's talk about let's start here. I'm starting with this because this seems like a very popular comparison. Like whenever people are talking about rasterization versus ray tracing, they start with this image. It's super popular. I believe this is from an earlier Intel presentation, but I'm not 100% sure. It may not be. I'm not sure exactly what the source of this image is, but people like to start with comparing rasterization and ray tracing, and I'm going to start there as well. I'm going to use the same image. And you see, like rasterization, just primary visibility here, and pretty much nothing else. Over here in ray tracing, we have nice shadows, we have reflections, and everything's looking much nicer. Although this is a little bit misleading because we know, you know we can do a bit more than just this with rasterization. Right? We did this in this class. We showed, for example, how to do reflections. Right? So it's not like we don't have any reflections in rasterization. It's just they're computed differently. They have certain limitations. Shadows. It's not like we don't have any shadows with rasterization. Right? So this is a little misleading. Yeah, true, but a little misleading because there are things that we can do in rasterization to make that a bit better. But what's happening today is that when we think about how people use the ray tracing support on the GPU, it's not ray tracing versus rasterization. It's more like rasterization plus ray tracing. Right? So that we're combining rasterization and ray tracing. That's how it's used in practice today. So here's a scene from a very recent game, Cyberpunk, and this scene is rendered using two different techniques. So one of them is using just rasterization, the other one is using rasterization plus ray tracing. I'm not showing you which one is which. Looking at this image, can you tell? Now, ray tracing is supposed to be a huge deal, right? And it is a big deal. But just looking at an image like this, it's not immediately obvious which one uses ray tracing and which one doesn't, right? Because there are things that we can do with rasterization without using any ray tracing at all. That produces this somewhat comparable image. But I'm going to say that this is also a little bit unfair. But can you tell which one's which? Soft shadows? Yeah, it's difficult to tell. You might be surprised, but this one has ray tracing. This one is computed using without ray tracing. Well, without GPU, without RTXs, without VXR is what I'm trying to say. This is, I believe this is using screen space ray tracing, so it's some sort of ray tracing, but it's more in the raster context. It's not using like pure ray tracing. But you can't, if you look at this image, and this doesn't quite sell ray tracing, right? Obviously, you might even arguably prefer this one over this one, right? It's kind of, yeah, maybe you like these crisp reflections, they look really nice here. Maybe you think that reflections are supposed to be a little bit blurry, and it becomes a matter of taste in a way, right? So this is not a fair comparison either in the context of like showcasing ray tracing. And the reason for this is that these games that we have today, they're not really designed for ray tracing. Ray tracing is oftentimes added like an afterthought. It's not necessarily an afterthought, but if you imagine their user base, most people playing these games will be seeing this. Like they will be running those games on hardware without hardware ray tracing support, right? So most of the players will see this. So if you are a game developer, of course you're going to sort of optimize your production process for this. But then you want to give a little bit of extra for people who have access to hardware ray tracing, so you add stuff on top. So it's very different in the sense that you can't just get something that doesn't look right without ray tracing, right? You kind of need to develop your scene accordingly. That's why this is not a fair comparison for ray tracing. But with ray tracing, though, today we can do really, really amazing things. Like this image is rendered using a very large number of light sources. I don't even know how many, and it's just looking gorgeous, absolutely gorgeous. Like this kind of lighting would be very difficult, very, very expensive to compute using rasterization. Because if I were to use just rasterization only techniques for an image like this, and if I have a lot of light sources, I'm going to have to compute a lot of shadow maps, right? And that would be very, very expensive. It wouldn't be fast at all. But with ray tracing support, we can't do that. So today, what we do is that we handle primary visibility with rasterization, and all the secondary effects like shadows and reflections using ray tracing, right? Nonetheless, you look at this image, it looks great. I love it. It's absolutely gorgeous. But it doesn't look like it's a photograph, right? It's not real. And you can tell this. It still looks a little bit CG. So that's the thing. Like with ray tracing, we're supposed to break that CG look completely. We're supposed to get something that looks like real. We're not quite there yet. There are multiple reasons for that. Like one big reason for this scene specifically is that probably these materials could be improved. So yeah, ray tracing improves the lighting and shadows and reflections, but the material definitions probably require a little bit of improvement here. But there's a lot more. Like going from here to something like this with offline ray tracing. Now look at this image. Honestly, I know that this image was rendered using Arnold, but I don't know what part of this image is real, what part is CG. It's like, I really don't know. Look at this image, it's like impossible to tell. But this is offline ray tracing, right? So this is really using ray tracing to its full capacity. So eventually, this is where we want to end up with interactive rendering, but we're not quite there yet. And I'll explain why that is the case. So we're going to talk about GPU ray tracing today, and basically what I would like to cover is why. Why do we want GPU ray tracing? Why is this a big deal? It's a huge deal, and why is that? How does it work? How is the hardware sort of structured, like the ray tracing pipeline is structured? What can we do now, and what should we expect the future to look like, possibly throughout your careers? All right. That's going to be our topic. So let's start with, again, going back to rasterization versus ray tracing. So you see that in this course, I've mentioned ray tracing a lot, even though our main topic has always been rasterization, right? Because the GPU we're using for interactive computer graphics is designed to do rasterization. But I kept mentioning ray tracing because it's everything that we want to do with rendering. We kind of have to, we end up looking at ray tracing in some way or another. So these two algorithms are actually conceptually very similar to each other. It's just like the inverse way of looking at things. So it's like, you can think of this rasterization as like a nested for loop. Like for each primitive, you find the pixel samples. That is, for each primitive, for each pixel, right? Sort of. With ray tracing, it's like for each pixel sample, for each pixel, you look at the primitives, you find the closest primitive. So it's like for each pixel, for each primitive. So it's like the same nested for loop, but in the inverse order. It really looks like that from a distance. So it's okay to think about ray tracing and rasterization as like the opposite operation. So rasterization starts with the triangles that we want to render and goes to the image, and ray tracing starts with the samples that we have and binds the triangles, right? So let's remember how these two algorithms work in the context of primary visibility. So with rasterization, I have my triangle, and I'm going to project that triangle and find it where it is in the canonical view volume that's been on the screen, and I get my next triangle, and I then find its position on the screen, and with using Z-buffer rasterization, I can figure out which triangle is in front of the other, right? So that's how rasterization works. With ray tracing, we went over this before. We start with having our scene, our entire scene, and then we're going to, actually we don't even need this linear scene, canonical view volume kind of stuff at all. So with ray tracing, we don't need that. Well, what I need to know is where my sample is on the screen that I'm interested in, and so I can send a ray through it, and that ray, I'll traverse that ray, and I'll find the hit points with the first hit point on a triangle or a scene primitive, and then I'm going to shade that point, right? And if that triangle is semi-transparent, I can just continue. right? I can take this ray and continue and find the next one. So this handling transparency becomes something super easy in the context of ray tracing. Right? It's really nice. And if I want to form an image, I just need to send samples through each one of my pixels, and in the end, I have my image. But we said the power of ray tracing is not about primary visibility. Like rasterization is about primary visibility, but ray tracing can do more, right? With ray tracing, yes, we can generate a primary ray and send it through the scene and find a hit point, but we can also, at that point, we can also send secondary rays, right? Like a secondary reflection ray, and by tracing that ray and finding the hit points, we can actually compute reflections. We can actually properly compute reflections. So we talked about this, and ray tracing shines with its ability to do things that are just way beyond primary visibility. Like we can handle reflections, refractions, and shadows, and realistic illumination that is global illumination. So that's where ray tracing really shows extra advantages over rasterization. So that's one reason why we want to use ray tracing, right? So we want to do shadows. Yeah, we can do shadow maps. Shadow maps work. Like we can define the position for any point on the depth map and figure out where the shadow is, and we can get some shadow that looks like this, and that would be fine. But with ray tracing, we can actually improve this quite a bit because we're not going to have, we won't need to pre-compute a depth map with some resolution. Instead, we send shadow rays, and with those shadow rays, we can actually compute these hard shadows in a very nice and crisp way. Look at this, right? So we can have very sharp shadow boundaries if you're using ray tracing. But maybe you think that shadow maps are good enough. Maybe you don't mind. Okay, for point light source that works. But how about area lights? When I have an area light, I'm going to have an area shadow, right? With rasterization, that doesn't work so well, right? With shadow maps. But with ray tracing, I can just send rays to my area light source at multiple different locations, and by doing that, I can figure out which portion of this light is covered at any point in the scene, and that will give me nice soft shadows. But with ray tracing, I can do that. I can sort of fake soft shadows with rasterization-based approaches. We talked about a couple of them. There are others, but they're not going to be perfect, right? They're sort of okay. They produce something that looks soft, but they always have one problem or another. Right? Same goes with reflections. We can do reflections with rasterization. We use cube map reflections, for example, for objects. I showed you how to do this, right? So we're rendering faces of cube maps, but this is not going to be the right reflection, right? This is going to be sort of fake because this cube map reflections, they're only correct for this one point in the middle of this object, but it's going to be incorrect for any point on the surface. Actually, even for this point, it's not reflecting the teapot itself, so there's no reflection of the teapot itself on the teapot, which is sort of weird. It's not what is supposed to happen. So like I can see the reflection of the spout here, I can see the reflection of the handle back there because, well, it's not in my cube map, right? But if you use ray tracing, you can actually see these. You see that the reflection of the handle is over here. So I'm going to show you a few images from the teapot rendering competition from prior years. Some award-winning images you'll see throughout this lecture today. So, all right, this is a little subtle, but it's important for it to be there. Here's another example where the reflection is less subtle. You can actually see it. I mean, you may like it or you may not like it. Nonetheless, it's supposed to be there. That's how reflections work. So, but maybe with simple objects, we could handle reflections of this sort. Maybe. Yeah, this is with ray tracing. It's computed using ray tracing, so these are proper reflections. But maybe these edges will be a little bit problematic. But most of the surface maybe we could handle, right? But remember, these are perfect reflections. That is perfectly smooth surfaces. What if the surface is not perfectly smooth? If the surface is not perfectly smooth, then the reflections will look more like this, right? So handling something like this for an arbitrary object, that would require using ray tracing if you were to compute this properly. Of course, we could try to fake this by trying to blur the reflections, but it's not going to be exactly the same, right? And with ray tracing, we can render something like this, but also we can evaluate materials. Like in this case, it's polished aluminum, I believe. But if it's brushed, this is what it's going to look like, and we can actually properly compute this using ray tracing. That's where the advantage is. So can we fake this using rasterization? Probably we can produce something that kind of maybe looks like something like this, but that would be a lot more involved and it won't look exactly the same, obviously. So you always lose some quality when you're trying to fake something like this. Well, how is this even helping? Like where's this coming from? Like, this is all related to the rendering equation. We talked about the rendering equation a lot in this course because the rendering equation is the incoming light to a point, and the incoming light is going to be the sum of direct illumination coming directly from the light sources and indirect illumination, right? Indirect illumination, that's basically reflected light off of the objects. And we oftentimes separate the two and handle direct illumination and indirect illumination as separate integrals, as sum of two separate integrals. For handling our reflections, remember, we did a trick. We changed this BIDF. We changed this material function, and we replaced it with a delta BIDF. With delta BIDF, things simplified because delta BIDF was 0 for all of these directions except for this one perfect reflection direction. So with perfect reflection direction, we basically got rid of this whole integral, and everything collapsed into just this one light coming from one direction. So we could sort of handle things like smooth reflections like this. But if you were to compute materials, if you were to handle materials not that smooth, still have strong reflections, but not smooth, then we have to do a bit more. That's not going to cut it, right? And these sort of materials are quite common in reality. They're actually all over the place, right? Not every reflective surface we have is smooth. And almost all of the surfaces that we encounter in daily life will have some sort of reflection. Some of them will have very obvious reflections. Some of them will have more subtle reflections. And oftentimes those reflections are not going to be perfect. So the same goes with refractions, right? With smooth surfaces, maybe we could handle them with some image space refraction techniques, but materials like this are a lot harder to handle. Right? So like in a scene with all sorts of complex materials, you really need to use ray tracing to get the image quality that you want, right? But going back, yeah, soft shadows versus hard shadows. With rasterization, hard shadow, maybe we could just blur it a little bit. It doesn't look quite exactly the same, right? But we were trying to get an image that looks sort of similar. And with reflections, yeah, we could do this like with perfectly flat objects or with cube maps. If it's not perfectly flat, maybe we can fake it, but we're not going to get exactly the same thing. Right? We could still do something with rasterization. With global illumination, right? So we could compute global illumination with ray tracing. We could actually global illumination. We're stuck. We don't have a rasterization-based solution for global illumination at all. So this is actually all right, let me rephrase it. We don't have good rasterization-based solutions for global illumination. There are solutions, yes, and I'll show you one, but they're not necessarily good ones. So we're kind of stuck with ray tracing. Now this is real-time global illumination. Yes, computed on the GPU, but it is using GPU ray tracing. So there's ray tracing in here. Okay. All right. So let's see let's see the graphics pipeline and GPU graphics pipeline and how this whole thing works. Right, so rasterization pipeline, you guys are familiar with this. Let's, we have some input primitives, they go through vertex processing, vertex purge, we can have a tessellation shaders, we can have geometry shader, whatever, some vertex processing happens here, some rasterization comes after that, and then we have fragment shader, and then we have our final image. So you might expect the ray tracing based pipeline on the GPU to look similar. It doesn't look completely dissimilar, but it's not quite like this, right? It's not like we're just sending pixels and then we just generate some rays, and then we have some hardware supported ray tracing happening in between, and then we have hit miss shaders, basically equivalent of fragment shaders like computing color, and then we have final image. It's kind of like this, but not quite. Not quite. So we're going to have to modify things a little bit to fit the way that ray tracing works. Actually, this could work. But the reason why the GPU graphics pipeline for ray tracing is not quite structured this way, it's like an exact replica of the rasterization pipeline. It's not quite like this because we want to be able to do more with ray tracing. So the goal of ray tracing on the GPU is not to take this pipeline and replace it with ray tracing. That's not the goal. We're going to use ray tracing in combination with rasterization, and we're going to use ray tracing mostly for secondary effects, right? Like reflections or like shadows. So the goal of ray tracing is not going to be just directly producing this image. So we're not going to spit out this image from whenever we compute these colors, but we're going to send it back to our ray generation. So whatever color we compute here is going to be sent back to whoever generated that ray. Because if we are generating a reflection ray, I would like to know that reflection amount coming from that direction. I send the ray, and I get the amount of reflection from that direction, and then I'm going to use it in my shading. So I need that color back here so I can actually use it, right? And I'm not going to directly output that color because that's not necessarily my primary visibility, right? That could be my secondary visibility. That could be shadows, right? So I need to know that, is this when I cast a shadow ray, I need the result of that shadow ray back from where I'm sending that shadow. So in the end, I'm going to get it back, I'm going to get all the secondary stuff back, and then I am going to produce my final image. So my final image is actually going to come out from here, like wherever I generated my rays. So that's what the ray tracing pipeline looks more like. Right, so let's take a look at the ray tracing pipeline in a bit more detail. So particularly what happens in here, this magical stuff. In here, in the ray tracing box, let me blow it up a little bit and show you what goes on in here. So that there's going to be some input and there's going to be some output. First, let's connect it here. So what's going to happen is that at first, when we send a ray into this ray tracing box, the ray is going to be used for traversing the scene. So it's going to go through the scene and find the primitives. How is that going to do that? Well, there's going to be some dedicated hardware support to help with this process. It will, of course, need to have some access to our scene definition. So this will need to know our scene, and I'll say a few more things about that in a little bit. That's why I sort of made this box a little bluish, right? Because it's like our scene definition is sort of softly included in there. So it is going to traverse our scene, and then it's going to check and see if that ray hits any of our scene primitives. Now for that, we're going to be using programmable intersection shaders. And the reason for having an intersection shader here and making it programmable is that sort of we can use any type of primitive that we want. So with rasterization, our rasterization pipeline is designed to work with triangles. Yeah, we can send lines, with tessellation we can send quads, but in the end everything is converted to triangles, and rasterizer handles triangles, right? It could be handling lines directly as well, for all we care, but the point is that it's not going to be able to handle generic primitives. But with ray tracing, one of the advantages of ray tracing is that we're not stuck with triangles anymore. We can actually handle more complex objects. For example, I can directly render a sphere without triangulating it first with ray tracing. Ray sphere intersection is fairly easy to compute. So you can have different types of primitives with ray tracing, and this intersection shader, this programmable intersection shader, gives you that support. So you can use it for ray triangle intersection if you want to, but this gives you the ability to have primitives that are not necessarily triangles, right? So that's pretty helpful in general. So if my intersection shader decides that, no, that ray actually is not intersecting with that primitive that I'm testing, then it's going to, of course, send it back to the scene traversal, and scene traversal will continue to find another primitive for that ray. And once it finds a primitive for that ray, that intersection shader returns, yes, yeah, I found a hit. Then the question becomes, well, is this the closest hit? Because, with primary visibility, actually even with secondary visibility, I would like to find the closest object along the ray, the closest hit along the ray. Is this the closest one? Or did I already find something? Have I already found something that was closer? Like earlier, maybe I found something that was closer, then this is further away, that means it's behind that object, right? I found a hit, and now I'm finding another hit that's behind that object, that means I don't care, it's not visible. So go back, it's not the closest, so I don't care. If it's the closest, that is good, then I found something that I'm supposed to shade, right? But remember, one of the advantages of ray tracing is that we could handle transparency really well. So let's see if this hit, this object that was hit with the ray is opaque. If it's opaque, then it's fine. Then I can say, okay, I found my hit point. I found my hit point, then I'm done. Well, not quite. I found a hit point, and so far this is the closest one. But maybe as the scene traversal continues, I will find an even closer one. So I need to go back to the scene traversal and continue traversing the rest of the scene to make sure that there's not going to be anything that is closer. Right? So if this is opaque, that's what happens. If this is not opaque, that means it's semi-transparent. So I'm going to look at this any hit shader. So the any hit shader will determine what to do with that hit. I can say, oh yeah, I'm going to use this to just replace and update my hit data. I can do that. Or I can say, you know what, this was actually, I can use it for alpha testing, for example. And I can say, oh, actually from here you're not really quite seeing anything, so I can just pass it back to the scene traversal and ignore that hit. Right? So this is what the traversal looks like. So it's a bit more complicated. And with two programmable pieces here, there's going to be this intersection shader and any hit shader if we have semi-transparent objects. Right? And in the end, this hit data will stay here in the ray tracing box, and the scene traversal will need to send it to the next stage in the end. So like this is the hit that we found. That is if we found a hit. That's why this is called hit or miss shader, and that's why I'm calling it hit or miss shader. Because maybe I found a hit with an object, maybe I didn't find anything, maybe it was a miss. Right? So basically in this ray tracing box, I have two programmable shaders here. I have an intersection shader and a hit shader. And over here, we have actually not a combined hit miss shader. We have a hit shader and a separate miss shader. So if it's a hit, then the hit shader is called. If the ray does not intersect with anything, then the miss shader is called. And the result is sent back to the ray generation. So basically, you look at it and you see that seems like we have 5 new shaders, right? Ray generation shader, intersection shader, any hit shader, and miss shader. With the new tier of DXR, DirectX ray tracing, tier 1.1, I believe, now we have inline ray tracing. So you can actually start tracing rays from any of your shaders. Even in a compute shader, you can start ray tracing. You can generate a ray and tell it to traverse that ray and trace that ray, tell your GPU to trace that ray, and GPU will trace that ray and send the result back to you, right? So you can use it inside pretty much any shader today. Right? So that's what the ray tracing pipeline looks like. And we can use this. So as you can see, I'm not showing an output image here. You can use it however you like. So this is hardware-supported ray tracing to accelerate ray tracing-related computations, and allows you to have programmable components here and there. And what's important is what you're doing here. Like inside your shader, you are using ray tracing to do something. And this is totally up to you. So you can use this ray tracing pipeline to do whatever it is that you want with ray tracing. Right? So that's where we're going to be using it, and that's how we can combine ray tracing easily with rasterization, because I could just call it from, let's say, inside my fragment shader. In my fragment shader, I can generate an array and just run this and get the results back into my fragment shader and continue processing my fragment shader. So inline ray tracing. All right, so that's what the GPU ray tracing pipeline looks like. Let's go back and expand this box, because I want to go back to talking about this. So we said that this box, traverse scene, is going to have to figure out a way to access our entire scene, right? So somehow I'm going to send the GPU my scene definitions, because I'm not sending one triangle at a time now, right? I'm going to have to put my scene into some data structure that the GPU recognizes, and then the GPU will access the parts of that data structure as needed, right? And there's actually quite a bit more going on here. This part is not all that simple. So let me explain why. How do we ray trace a particular scene? Let's say that this is our simple scene, just a teapot, and I have my ray. I have one ray. I have one ray to trace, and I'm going to figure out which triangle of this teapot this ray intersects with, if any. Maybe it's not going to intersect any of them. Maybe it'll intersect one. So we'll see. So but I have a lot of triangles here, right? Quite a few triangles. So the brute force thing to do would be to test the intersection of each one of these triangles against this ray. We can do that. But this doesn't scale that well, because I might have a lot of triangles. I might even have millions of triangles, and I might have millions of rays. So that would be quite a massive computation. So I need to find a way to accelerate that computation. And we can do that. For example, if I know the bounding box of this teapot, it's this bounding volume. There's a box, the axis-aligned box, that covers this teapot, and this teapot is perfectly contained inside this box. Now, if this ray does not intersect with this box, there is no chance, not a possibility, that it will intersect with any triangle inside the box. Right? It's obvious. If the ray does not intersect with the box, it's not going to intersect with anything that's inside the box. So for it to intersect with anything inside the box, it needs to intersect with the box first. So by doing just this very simple computation, I can actually save a lot. Like just by adding a box to my object. Now all of these rays that would obviously miss the teapot because they're not even intersecting with the box, I can get rid of them. I don't even have to compute them. So that saves me a lot of computation. Now we can take this idea and take it a step further. I can take my teapot and, let's say, split it into two. So now I have two boxes, and I can check against these two boxes. So if my ray does not intersect with any of the boxes, then I can throw it away. Or if my ray intersects with only one of the boxes, then I only need to check the triangles inside that box. I don't have to look at the other box. Right? I can do this further. Right? I can split this some more, and now I have more boxes to check. But then it gives me a better level of isolating where that ray could be hitting a triangle. And I can do more. I can split it more. At the limit, I have lots of boxes. But of course, now the problem becomes, now I have a lot of boxes to traverse. So I don't want to do that. Instead, what we're going to do is we're going to build a hierarchy from this. So bounding volume hierarchy. We're going to have all of these different levels of boxes. So at the very top, I have this one bounding box. At the next level of the tree, I have, let's say, two bounding boxes. One branch is for one of the bounding boxes. The other branch is the other for the other bounding box. So there's a root node, a child node, and a child node of the child node. So it goes all the way down to however deep that you need it to be. And using this bounding volume hierarchy, or BVH, we can accelerate ray intersection quite a bit. So now bounding volume hierarchy is just one data structure, and this bounding volume hierarchy forming a tree with two child nodes for each internal node is a special kind of bounding volume hierarchy. It's a specific kind of bounding volume hierarchy. There are different other kinds as well. But this is the most common structure used for accelerating ray tracing today. But there are, I'm telling you, there are other acceleration structures that could be used with ray tracing. Now, what exactly the GPU does under the hood, the thing is, we shouldn't care. We probably shouldn't care. I mean, it should be good enough, and the hardware would be optimized for that particular acceleration structure, and we'll do a good job in the end, where we're hoping. And we don't necessarily need to care about the specifics of the acceleration structure. But yeah, it is a BVH, but it didn't have to be, is what I'm trying to say. Now, if you have a good acceleration structure, what happens is that even if you have millions of triangles in your scene, your ray you'll test intersections of each ray with, let's say, about a handful of triangles. Because with a whole bunch of boxes in a hierarchy, and just a relatively small number of triangles. It could be just 3, 4, it could be 10, it probably shouldn't be 20 if your acceleration structure is good. So in the end, this is called acceleration structure because it really accelerates ray tracing. Like imagine the comparison between testing ray intersections with a million triangles versus, let's say, 5. Right? There's a huge difference in terms of performance. This is really what helps ray tracing run as fast as it does today. Very, very, very important. Yeah, a comment here is about KD trees. Yes, KD trees were very popular back in the day. They're not as popular today. I really don't want to get into the details of KD trees and why BVHs are preferred. It's a very long conversation. It's kind of, yeah, it's going to be a very nuanced discussion, so I don't want to get into that. But BVHs are what we prefer today. But there might be others that we prefer in the future, maybe. We'll see. Actually, about that, we recently proposed a different acceleration structure that looks very much like BVHs. It is also called space partitioning structures because they split the space into partitions. So we propose a different structure that looks very much like DVH, and if you have hardware support, it actually runs much faster. So yeah, maybe we'll have different acceleration structures in the future. So yeah, so this is what GPU ray tracing support looks like, and with that, we can compute global elimination. Right, so now when I say global elimination, people immediately think about path tracing. Remember path tracing? We talked about path tracing. We actually talked about a whole bunch of different ways of computing global elimination on the GPU. Now this is not quite path tracing. This is using the visual lights idea that we discussed last time. So this is tracing some rays starting from the original light sources to place some visual lights in the scene. And then of course there are some bounces that are happening in the scene as well. So there could be visual lights even places that are not directly seeing the light source. And then the scene is rendered using these visual lights and computing shadows and all that. Right, so maybe it might be obvious as to how we generate these visual lights for this kind of a problem. Yeah, you can see how ray tracing could work, right? Because we're tracing rays to find where to place the visual lights, and then we're tracing rays to figure out the shadows for those visual lights, right? But ray tracing is a very general concept that we use in rendering. When we use it for sampling, we oftentimes use it for estimating this rendering. So you look at this equation, it's an integral, and it's not immediately obvious how ray tracing could help you with something like this. And it helps you with sampling. For example, if we are trying to compute the area lights, or an area light like this, we could just pick some random samples on this area light surface, and then we can trace shadow rays. And with that, we can approximate the shadow. So that's going to be the idea, that we're going to be approximating an integral by using a finite number of point samples, because that's what ray tracing will do. So basically what's going to do is going to take this integral, and it's going to approximate it as a sum of finite number of elements. Okay? So this is integral converted into sum of, or an average of n samples. Now it's a bit more complicated than this, because how you pick your samples becomes a little bit important. I'm sort of skipping some of the details, like important sampling, which is super important. But I'm skipping all those details. But basically, this is the general idea, that you convert this integral to an average like this. Now, if it's not obvious to you how this works, let me show you. You can think about, like, yeah, this looks like a complicated equation, but it doesn't matter. Let's represent it as something simple. Let's say this whole thing is f. Okay, that's f, and I would like to sort of approximate the integral of this f within some domain using a finite number of samples. Right. So f, let's say, is a function over x defined here, and let's say this is what f looks like. It's just a 1D function, and you can think about this process as like having a finite number of samples along x, and then you compute the value of f at each one of those points. Basically, this integral will give you the area under under f over here, and this is going to give you the approximated area. So I'm skipping some of the details in the math just to make it look simple, right? So in the end, this is what sampling with ray tracing looks like. So we have an integral, we're sampling it with a bunch of rays. Now the immediate question, I think, is what is n? How many rays? Well, it depends. For example, this image from the T-board rendering competition a couple years back. So I told Laura about this image. She used path tracing for computing this. And with path tracing, now I don't remember the exact sample count she used, so I'm going to make it up. I believe it was something like 10,000 samples per pixel. 10,000 samples, maybe it was 100,000, but I believe it was 10,000. Actually, maybe it was way more than 10,000, but that's why I remember it was 10,000. And that was really needed to resolve some of the details here. 10,000 samples per pixel. This is not 10,000 rays per pixel, mind you, because each ray will go through refractions and reflections. So each sample will go through all these reflections and reflections. So each sample per pixel will correspond to on the order of maybe 10, maybe 100 rays per pixel. So even if this is 10,000 samples per pixel, it's probably more like 100,000 to a million rays per pixel. That's a lot of rays. A lot of rays. Can we do that? And why do we need this anyway? Because here's the thing. If I just use one sample per pixel with path tracing, I get a noisy garbage like this. Right? And this is using some very nice sampling techniques. So like the important sampling, as I mentioned, this is actually using very nice sampling techniques, but still it's super noisy, right? I can increase the sample count to, let's say, from 1 to, let's crank it up, 1,000. Looks much better, right? From here to here, it looks so much better with more samples, but we're not quite done. You see the interior? In here, and there, it's still pretty noisy. Like in some places, it worked out okay. There's still noise around here. It's not perfect, but yeah. So maybe crank it up some more. Let's say, I don't know, 8,000. So it's getting better, right? So with ray tracing support, people immediately imagine path tracing. Like, let's do path tracing on the GPU. But this is the cost of path tracing. Now we can afford it for offline rendering, and that's why almost all offline rendering we have today for like movies, special effects, it's using path tracing because we can't afford this. We can have lots and lots of rays per pixel. But this is what we want. This is what we're doing on the GPU. And with this, how many rays do you think we have per pixel? We definitely don't have 10,000. 1,000? It's not even 10. I think we can sort of expect to get maybe 1. And if you're lucky, maybe 2, 3. I mean, beyond 4, you're sort of pushing it. It's going to be way too expensive. So yes, we do have ray tracing support on the GPU. But this doesn't mean that we can just do everything with ray tracing because we can't afford that many rays. Right? We only have a limited number of rays. So that means that what we can do with ray tracing is going to have to be limited. Right? And so typically what we have in games today is about 1 ray per pixel, maybe 2 rays per pixel. Oftentimes it's even less than 1 ray per pixel. Because that's what we can afford. Because that's what runs fast. And that's why we need rasterization in here. We can't just ditch rasterization and say, I'm going to do everything with ray tracing because, well, rasterization counts for at least 1 ray per pixel. Like for the center primary visibility, it's handling that. If I use rasterization, that means I'm going to use 1 less ray per pixel. And then I have very few rays per pixel, so it's kind of important that I do that. But you may think, okay, with 1 ray per pixel, 1 sample per pixel, 1 ray per pixel, can I even do anything with it? Like if I were to compute some really relatively simple soft shadows with 1 ray per pixel, that's 1 ray sample per pixel. I get something that looks super noisy. And that's sort of understandable, right? Because imagine that I have this area light, and I'm going to estimate how much of this area light I'm seeing by sending one ray. I mean, that doesn't even make any sense, which is one ray, because that one ray is going to say, yeah, you see all of the light, or you'll say, you see none of the light, and there's nothing in between. So obviously we're getting noise. I mean, what else, right? So there's some probability going on here. So the probability of a random ray going to an area light, hitting something on the way or not hitting anything on the way, depends on where you are in the shadow, yes. So this noise sort of indicates where you are in the shadow, but it's still super noisy. So what can we do? What we're going to do is going to be denoising. Yes, so we're going to take this image, generate it with as many ray samples as we can afford, typically just one, and then we're going to run a denoiser. And the denoiser is going to work on the image space, and it's going to basically blur out all these regions, and you're going to get an image that looks like this, right? So we go from here to here. It's quite an improvement, right? In the sense that we got rid of the noise. Yeah, we got rid of the noise, and the latest denoisers are actually pretty good. Yeah, I call them, like, they're like magic, really. Like, you can give an image like this with lots of noise all over the place, and then you can get an image that looks like this. Right? It's like magic, in a way. But, of course, we are not computing this image with all these rays. So all these subtle details that we would get if we were to actually compute this image, they're all lost, right? So with ray tracing, what we can do today is going to be rasterization plus ray tracing plus denoising. And we can really generate images that look, this looks beautiful to me. I love this image. And we can generate things like this that we couldn't before. But at the same time, we kind of need to understand that there's going to be a limit to what we can do, because yeah, with rasterization-related techniques, when it comes to reflections and refractions and shadows, we were sort of approximating a lot of things. With ray tracing support, we're sort of computing them, but we're not really computing them because we don't have enough rays to compute them. So we are doing this denoising in the end. So we are sort of approximating the actual computation in a noisy way, and then we are having this denoising pass, so we get something that is usable, right? And that's the reason why, that's one of the reasons why when you look at images like this, they may not look perfectly real because we're not actually fully computing them. We're sort of approximating them, right? That's one of the reasons why the images that we see generated using rasterization plus ray tracing on the GPU, even though we're using ray tracing and we're sort of expecting everything to look just real, they don't quite, because we don't have enough rays, and we're sort of using this denoising step to make things look okay. Now, I'm going to show a reference here. This is a SIGGRAPH 2018 course, Introduction to DirectX Ray Tracing. If you're interested in implementing ray tracing, I would really highly recommend that you check it out. The video is available on YouTube. You can watch the entire I believe, 3-hour course. And here's a link. You can find this course in this link under Chris Wyman's webpage. I would really recommend it if you want to implement ray tracing. Go and check out that course. It's excellent. It covers the basics of ray tracing as well as all the details of the API and the writing shaders and everything. So I would really recommend it. All right. So this is what I wanted to cover regarding where we are today. Now, I also want to say a few things about what we should expect the future to look like. Now, any prediction of the future is sort of doomed to fail because there are things that maybe you can predict certain things, but definitely you cannot always predict everything, and some things can be big game changers. So I'm going to say a few things, but before I say anything, I just want you to take it with a grain of salt, because I know that there are only certain things that I can see, and there are things that I won't be able to see. So my predictions of the future maybe quite off. So we'll see. Maybe I'll be spot on, but maybe I'll be really off. But I'm going to base my prediction on a history. This is oftentimes a good idea. If you see how things worked in the past, that might give you an indication of how they might work in the future. And I think the history of offline rendering is a very good indicator of what we should expect to see in interactive computer graphics in the next decade or so. So in offline rendering in the past, ray tracing was in a similar state. We were using in the early days, we weren't using ray tracing at all with offline rendering. Everything was just rasterization. It was not Z-buffer rasterization necessarily. We were using A-buffer because A-buffer could do transparency a bit better than Z-buffer, quite a bit better than Z-buffer. So it had that advantage. But beyond that, there's rasterization-based algorithms. Pixar's RenderMan has been using Reyes, again, another rasterization-based algorithm. So we had rasterization, and in the end, we added support, ray tracing support, just a little bit of ray tracing support for handling reflections, for handling refractions. And then we extended that ray tracing support a little bit. And then in the end, we started computing global illumination with ray tracing support. Actually, talking about history, I just want to mention the history that relates to me, that I implemented a render for global illumination back in 2002, 2003 when I had implemented this part of my master's thesis, and then I published it much later. So this is a global illumination-based rendering. So there's just one light source in the scene. Everything is illuminated by a single light source, and the whole scene, pretty much the whole scene, is rendered using indirect illumination. And there's no ray tracing here. This is pure rasterization. And I'm telling you, this is a bad idea. Don't do it. Back then I thought this was, ray tracing is too slow. We can't do ray tracing, so let's do everything with rasterization. That was my idea. I did that. But I think if I were to do this in ray tracing, it would have been faster, even back then. So not necessarily a good idea. What I'm trying to say is that even for offline rendering, ray tracing was really, really slow at first. So we didn't quite use that, and we started doing stuff. We started adding things as we needed them. So we started with rasterization using A-buffer or Reyes, and with reflection maps. So if you want reflections, we were computing reflection maps, just like the render to texture tricks that we've been using in this course. They were used in offline rendering back in the day. And then we had some ray tracing software. So we had, of course, software. So we started using rasterization plus ray tracing. So with perfect reflections and refractions, we could use ray tracing. And with hard shadows, instead of computing shadow maps, we could use ray tracing, right? So this is very close to where we are today with real-time rendering. But that's where offline rendering was about 20 years ago, approximately. That's where we were. And of course, we had a few other things. Like maybe we could do soft shadows and global illumination. And so what happened what happened is that as the rendering software evolved and computers became faster and faster, we moved from rasterization-only approaches to rasterization plus ray tracing, and then to ray tracing only. And ray tracing only. And today we're using ray tracing only. We sort of ditch rasterization completely for offline rendering. For the most part, rasterization is very, very rarely used. Almost everything is rendered only with ray tracing, including primary visibility. And let me tell you why that is the case. So let's go to a comparison between rasterization and ray tracing. What would I use for anything? For primary visibility, what would I use? Ray tracing or rasterization? I can use both. They can work, right? For shadows, what would I use? Ray tracing or rasterization? Well, yeah, I can use both, but shadow maps, they will have resolution-related limitations. They won't be able to handle area lights very well. So maybe with shadows, we want to stick with ray tracing. Ray tracing will give us better shadows, no question, right? Reflections are reflections. I can use rasterization if my object is perfectly smooth, then if I'm okay with approximating it. But for general reflections, especially for surfaces that are not perfectly smooth, I would be using ray tracing, right? I want to be using rasterization. For global illumination, well, I have to use ray tracing. There's nothing else. Okay, so look at this picture. All of this stuff, I need to use ray tracing. Primary visibility, I can use rasterization or ray tracing, right? Now here's the thing. When you have enough rays to compute these things to the quality that we want, what is one more ray to handle this? If I'm going to have, let's say, 1,000 rays per pixel, what is 1,000 plus 1, right? I can just use 1,000 plus 1 and get rid of this. And then everything becomes ray tracing. And when I do that, then I get rid of all of the limitations of rasterization. Now, all of a sudden, my polygon count, my triangle count is not a big deal because I'm dealing with ray tracing now. And I don't need to worry about transparency. Transparency is very easy to handle. I don't have to worry about transparency at all, right? So my prediction for the future, based on this picture, is that when ray tracing is going to be fast enough, so we can compute global illumination using the techniques that we want to compute, so we have, I don't know, on the order of 100 to 1,000 rays per pixel, and we can handle that. Then I'm going to say we probably won't need rasterization, except for maybe some special cases. There might be a few cases where rasterization will be just perfectly fine. It doesn't take that much area on the GPU chip, so maybe it's okay to keep it around. But I'm expecting the graphics API for interactive graphics to be mostly, if not purely, on ray tracing. When the hardware is fast enough. So when is it going to be fast enough? Well, maybe for that, we need to look at hardware that is designed for ray tracing and ray tracing only. So today's GPUs are designed for mixed rendering, rasterization plus ray tracing, because with only ray tracing, we can't do as much as we want. It's very limited. But we are looking into that. At the University of Utah, we have a hardware ray tracing research group, and we're designing the future GPUs around ray tracing only. And we're sort of modifying the ray traversal software, and we're modifying ray tracing from a software perspective and in ways that make no sense for existing hardware. But then we're designing hardware that's specialized for handling that sort of ray tracing, so we can have super fast ray tracing-based GPUs that can only do ray tracing and nothing else. So that's one of the research projects going on at the University of Utah. And who knows, maybe in the future, not so distant future, we'll get there. I'm hoping within the next decade that we won't have to use rasterization at all for interactive computer graphics, and everything will be ray tracing. Because I think it's objective to say that ray tracing is vastly superior to rasterization. It's just that we have very super fast hardware for rasterization that our ray tracing hardware currently cannot compete with. And without that super fast rasterization hardware, we would not have interactive computer graphics. So don't undermine rasterization. This is how we have interactive computer graphics. Without that, we wouldn't have interactive computer graphics. We had interactive ray tracing for a couple of decades now, but they're not delivering the performance of rasterization. So interactive computer graphics still stands on the shoulders of rasterization. So we are in a very interesting place in computer graphics. Now I gave you this history of where things were at on offline rendering, and I'm trying to draw some parallels, but it's not possible to draw direct parallels because computer graphics evolved. We have much better algorithms than we didn't have before, back when offline graphics was dealing with similar issues in terms of performance. So we can do a bit more with the ray tracing capability that we have on the GPU than we could do in the past with similar form of limited ray tracing that was available in offline rendering, because we have new algorithms, we have a lot of new inventions, a lot of new and ingenious ways of using this limited ray tracing power that we have. And actually, over the decades, since the programmable shaders were introduced, people figured out all sorts of interesting ways of using this hardware, or dare I say, abusing this rasterization hardware to do things that it really wasn't designed to do. And with that, we could get all sorts of interesting algorithms, and we could do things that we couldn't do before. And in this course, we talked about a lot of those examples, actually. A lot of rasterization-based algorithms that use the GPU in ways that GPUs were not quite designed to do. And that was what we find. So now that we have ray tracing support on the GPU, it sort of gives us this additional tool that we can add on top of all the collection of tricks that we have in real-time rendering and interactive computer graphics. Now, ray tracing is an additional tool in our toolbox that we can do more. So we don't have to just take ray tracing and implement the same algorithms that are used for offline rendering. We can do interesting things with them. So yes, we can use them in forward rendering or deferred rendering. We can use them in our fragment shaders to do things that are designed for traditional ray tracing. But we can do other things with this interesting tool that's available now. And today is the time for those sort of inventions that are coming out every day. So this is the time for those sort of interesting things, interesting tricks to come out. And they are coming out. Okay. So I am going to end it right here. Thank you again for joining this interactive computer graphics lecture. Stay safe. Bye. Thank you. Oh, thank you. Thank you all for joining another lecture for interactive computer graphics. We're going to cover some interesting stuff today. It's going to be about transparency, blending, and alpha testing, and all that stuff that we're going to talk about today. That's going to sort of give us enough of a background to start talking about volume rendering next time. That's the plan. All right. So let's go ahead and start. Now, let's start with a question. Now look at this sphere. See that, right? Would you call this a transparent sphere? Now, I don't know, a lot of people would probably call that a transparent sphere, right? That is, I'm going to say that's not a transparent sphere. Let me show you what a transparent sphere looks like. It looks like, well, not quite like this. It looks like this. This is a transparent sphere. This, I think, from purely language perspective, it would be okay to call that a transparent sphere. In fact, that would be accurate to call that a transparent sphere. But in the context of computer graphics, when we say something is transparent, this is what we mean. This has refractions, right? And these refractions are very different to compute. So we call something like this typically a refractive sphere, a refractive object. So this is a refractive object, this is a transparent object. So what's really the difference? I mean, visually, yeah, there are no refractions here, there are refractions there. So it's not like this has a refraction index that is the same as air. That's not the point. It's just when you look at a transparent object like this, you should imagine something that has holes, like something that's porous that you can see through, something like this, right? You're sort of seeing through, of course, very, very tiny holes, and you're not seeing the holes, but you're seeing whatever's behind it. So you can imagine this as like see-through drapes, right? Something like this, like you can see through. That's what we mean when we talk about transparency. But of course, there are refractions. A lot of objects that we consider transparent in reality have refractions. Now, so today's topic is going to be mainly about transparency. That's what I said. But because these two things are related, I want to talk a little bit about refractions and how we could handle refractions. Because we talked about reflections, we didn't quite talk about refractions before. So let's cover that. Refractions. All right. So if refractions are real, then they should be in the rendering equation, right? that has been our motto, right? So you look at the rendering equation, refractions should be here somewhere. I'm looking at it, and honestly, I'm not seeing them. I mean, they're really not there at all, right? So the thing is, if there are any refractions, the refractions are not going to come from anywhere above the surface, right? It's going to come below the surface from down here, right? So we can actually include refractions in the rendering equation. We just need to extend the rendering equation just a little bit. Right? Instead of looking at a hemisphere, we're going to look at the entire sphere of all directions. So this becomes S square, indicating the surface of the sphere. So we're going to look at all directions, because light can be coming from anywhere. If it's coming from inside the surface, that's going to be a refraction, right? It's going to be refracted out, and we'll see it through the camera. That's the idea. And if it's coming from above the surface, that's going to be reflections. So yeah, okay, that's simple enough, right? And I changed this from FR, the reflection BRDF, to FS, that is BSDF, that's scattering, bidirectional scattering distribution function, because refractions will be scattered, right? So it's not just reflections, but it involves all sorts of surface scattering now. So this is the complete form of shading equation, all right? Rendering equation. Now, we're going to compute reflections and refractions a little bit differently, obviously. So we're going to do the same trick that we did before with everything. Like whenever we look at the rendering equation and say, I want to compute one part of it differently than another part of it, what we do, we take a rendering equation and we split it into pieces, right? So that's what we have been doing. We're going to do the same trick here. And the way we're going to split is, of course, we're going to look at this whole sphere. I'm going to split the sphere into two hemispheres. So the top hemisphere and the bottom hemisphere. That kind of makes sense, right? So the top hemisphere is going to be the one that we've been looking at so far. It's going to be the same thing. The bottom hemisphere is going to cover the refractions. So I can write my rendering equation as the sum of these two integrals. Top is the one that we had before. We just added this bottom one. That's the bottom half of the sphere. This is how I'm representing it. And it's otherwise the same equation. Okay, everything's good, everything's fine. All right, so one more thing we're going to do. Remember when we were talking about reflections? We decided to look at perfect reflections instead of looking at all sorts of reflections off the surface, because computing perfect reflections were a little bit easier because we had only one direction, right? So we assumed the surface was perfectly smooth, and when the surface was perfectly smooth, that sort of simplified the computation of reflections. Of course, not all materials are perfectly smooth, but this is for just making the computation easier. So we're going to do the same trick here. So I'm going to take this BSDF and convert it to a delta BSDF. Okay, so this is going to be like a perfectly smooth surface with refractions on it. So we know how to do the top part. Let's get rid of it. I'm just interested in this part, and that's going to be the light coming from the bottom hemisphere here. All right. So light is coming from everywhere, but I have this delta BSDF. That means so this is going to be non-zero only for the perfect refraction direction. Only for the perfect refraction direction for my view direction, this is going to be non-zero. Otherwise, it's going to be zero because it's a delta BSDF, because I'm assuming that the surface is perfectly smooth. In that case, I have this one direction that works. Everything else, I can just throw them away. I don't need them, and the integral simplifies to this little thing. Very good, right? For a smooth surface, this is enough. And how do we compute this direction, though? This refraction direction? Well, you must have seen how to do that using Snell's law. Like, we're going to look at the index of refraction outside. Let's assume that air is 1. Not exactly 1, but you can assume that it's 1, very close, actually. For index of refraction for